So we've proved that if p is a product of 2's, 5's, and something else, and that 10 has order k mod q, then the decimal expansion of 1 over p will have a k-digit repetend. But what if we work at a different base? It's important to understand that all steps of our proof work in any base. Consequently, our theorem generalizes if the greatest common divisor of q and p is 1, and q has order k mod p, then the base q expansion of 1 over p will have a k-digit repetend. So let's try and predict the number of digits in the repetend of 1/8 in base 5 and verify by direct computation. So we know the greatest common divisor of 5 and 8 is 1, so we want to find the order of 5 mod 8. So it's important to see that we're looking for the order of the base mod the denominator. We find that 8 has order 2, so this should have a 2-digit repetend. Now to find the base 5 expansion of 1/8, we want to find the coefficients in the expansion. 1/8 is a sum of the powers of 5. So note that by assumption the AIs have to be someplace between 0 and strictly less than 5, so this series is actually absolutely convergent, which, if it means anything to you, it means that we can do the arithmetic that we want to do. We don't have to sweat the fact that it's an infinite series. So let's split off that first term, and let's go ahead and multiply by 5 to allow us to solve for a1. Now, since 5/8 is less than 1, then a1 has to be 0. So now, splitting off the next term, we get, and this time if we multiply by 5 squared, 25, we'll get an expression in a2. And since 25/8 is between 3 and 4, then a2 is going to be 3. To proceed, note that so far we've found that 1/8 is 3/25 plus the rest of the infinite series. And rearranging, and doing a little arithmetic, and then multiplying by 25, we get. But we started with the series expansion of 1/8, so we have that 1/8, this series, is another series. And remember, to compare two series, we'll need to reindex them. If we reindex the right-hand side using I prime equals I minus 2, we get. And since we can call the index variable anything we want, we can conclude. And now we can compare the terms directly to find that AI is AI plus 2, which means that a repetend does have 2 digits. Now remember, 2 is an odd prime. Suppose we're working base 2. Then the greatest common divisor of 2 and q is automatically 1 for any odd number. And what this means is that any fraction p-qs with odd denominator will be non-terminating base 2. The repetend will have k digits, or we could call them bits for binary digits, when the order of 2 mod q is k. And so this raises the question, the worst case scenario is if 2 is a primitive root, and so when will 2 be a primitive root mod q? We'll take a look at that later.